Hello again. Now we're going to find the resultant vector given two different force vectors. And this could be with any type of vector, force vector, velocity vector, whatever. I'm just going to start off with two. However, no matter how many vectors you're finding the resultant of, it's the same process, whether you're doing it with 2, 20, or 200, or however many force vectors you have to, or vectors you have to work with. But if you look at the handout that's just simply labeled vectors, as far as its title, this is number 1 on that one. And I gave you a couple other examples that the answers are there, but I just want to work through this one with you. Here we're finding the resultant of two different vectors. 50 newtons, and newton is just the metric unit for weight, or for force, just like pounds is the English unit. 50 newtons at 125 degrees is F1, F2 is 39 newtons at 294 degrees. First thing I want you to do is to sketch the vectors. Now technically the length of the vector is representative of the magnitude, so the 50 newton vector should be longer than the 39 newton vector. So this F1 is 50 newtons at 125 degrees. So basically from 0, that's over to about 125 degrees. And F2 is 39 newtons at 294 degrees. So if we go from our positive x-axis, which is 0, all the way around, that's approximately 294. And again, we're sketching them. Just make sure they're in the right quadrant, and I'm happy. What I want you to do is I want you to chart this. We're going to make a chart where up top, for each of these columns, we're going to look at our horizontal and vertical components. Because what we're going to do is we're going to decompose each vector, F1 and F2, simply add the x's, add the y's, and that'll give us the resultant vector. But it has to be in what we call polar form, or the decomposed form. So F1, we take for the x value, or the horizontal component, 50 times the cosine of 125, we get negative 28.68. For the y value, take 50 times the sine of 125, you get 40.96. For F2, for the x component, a horizontal, it's 39 times the cosine at 294, we should get 15.86. For F2, the vertical component, is 39 times the sine of 294, you get negative 35.63. Now once you have each of them decomposed, you simply add your x's. Negative 28.68 plus 15.86 gives us a negative 12.82. And then you add your y's. 40.96 plus a negative 35.63 gives us 5.33. Now if you're decomposing, say, 3 or 4 vectors, you're just going to list them underneath it, and you'll be, instead of adding 2 numbers, you're going to be adding 3 or 4 numbers for both the x and the y. So however many vectors you have, that's how many x values you should be adding, and that's how many y values you should be adding. Now this is our resultant vector, but it's in polar form. We want to put, I'm sorry, rectangular form. We want to put it back in polar form, or like the form that we have the vectors given in. In order to do that, we simply have to convert back to polar. In other words, we have to find r, which is our magnitude, and we have to find theta, which is our direction. First, finding r is simply the square root of x squared plus y squared. So you're plugging in negative 12.82 for x and a positive 5.33 for y. You should end up with 13.88. It's pretty straightforward. But remember, to get to our direction, in order to get theta, we have to first find alpha. Alpha will always be a positive acute angle. To find alpha, it's the inverse tangent, absolute value of y over x. So we're just plugging into that formula. Inverse tangent, absolute value of 5.33 over negative 12.82. And remember, what does absolute value do? Absolute value makes everything inside positive. So really all we're doing is removing the negative from that 12.82. And that's how on the calculator we're always going to get a positive acute angle. So when you inverse tangent that, you get 22.58 degrees. That is our alpha. We're not done yet. We have to see what quadrant we're in and place that alpha in the correct quadrant. To know what quadrant we're in, we look at our resultant rectangular vector. We have a negative x value and a positive y value. Negative x means we go to the left, positive y means we go up, which puts us in quadrant number 2. So if we're in quadrant number 2, if you look at the chart I gave you, to find theta, theta is 180 minus alpha. So theta in this case is 180 minus 22.58 degrees, or theta is 157.42 degrees. So putting our r and our theta together, our overall resultant vector in polar form is 13.88 newtons at 157.42 degrees. Again, that's just putting the calculated values of r and theta together. We end up with those two forces acting at the same point, an overall resultant force of 13.88 newtons at an angle of 157.42 degrees. Now, let's put it back on the same diagram, sketch I should say, that we have of the other two vectors. So 157 degrees is going to be a little lower than that F1 vector, but we're also at 13.88 newtons, which is a lot shorter. So if we're at 157, that vector, the purple vector here, happens to represent it. So we'll say that is our resultant force vector of 13.88 newtons at 157.42 degrees. And I just put it below there because I ran out of room. But that would be a sketch of your resultant vector. Now again, no matter how many vectors you're finding, to find a resultant vector, you just decompose the x's, decompose the y's, add them up. Keep in mind, if you're given the resultant vector, say for instance I gave you the resultant vector and F1, and I looked for a component vector, in this case F2, instead of adding these, you would subtract from the resultant vector. In fact, you're going to have a problem or two that does that, so make sure you do the subtraction instead of the addition if you're given the resultant vector. In the next video, we'll look at vectors in equilibrium.